In late 1946, Italian engineer Cesare Pallavicino took over the technical department at the Argentine State Aircraft Factory in Córdoba. Back then, the facility was known as the Aerotechnical Institute. Pallavicino had arrived in Argentina that summer with a large group of engineers and workers. Most of them were from the Italian Caproni plants. Around the same time, Argentine Air Force Brigadier Juan Eduardo San Martin was putting together a massive production program. He oversaw national aircraft manufacturing. This newly arrived group of Italian specialists was exactly who he needed to help him pull it off. By November of that year, Pallavicino was handed an ambitious task. He was to design a twin-engine escort fighter. The aircraft was immediately included in the national 5-year plan. This made the project a major strategic priority for the country. The following month, in December 1946, Pallavicino presented 3 preliminary design concepts. 2 of them were jets, while the third was a traditional piston-powered design. The Argentine military went with the piston-powered option. They decided its projected specs perfectly met their requirements at the time. Work quickly kicked into high gear. Pallavicino immediately started putting together a special projects department overseen by a military officer. At first, the team was fairly small. The department was supposed to bring together experienced Italian engineers and new specialists who had just arrived from Spain. However, for the first 6 months, progress completely stalled. The main issue was a severe shortage of qualified aircraft designers. Pallavicino constantly pushed management for more manpower, but he kept hearing the same excuse. The institute simply didn't have anyone available at that skill level. At that point, his department had only 4 engineers and about a dozen draftsmen. Most of them lacked the experience for such a complex project. To salvage the situation, Pallavicino came up with a brilliant workaround. He transferred 4 of his top Italian engineers to the team. These were men who had worked with him for years and completely understood his workflow. Thanks to their massive experience, they could do the work of 15 or 20 average draftsmen. On top of that, he brought in a dozen talented young technicians fresh out of a technical school in Rosario, while keeping a few of the best local workers. With no more than 20 people under his command, all with wildly different skill levels, Pallavicino finally got full-scale development underway in July 1947. He had to take an unconventional approach. He trained the junior staff while designing and building the new aircraft at the exact same time. Despite all these hurdles, the first prototype was finished exactly 1 year later. This was a record-breaking pace, as developing an aircraft like this usually took twice as long. The new fighter was designated the I.Ae. It was also named Nancu, which means eagle in the language of the indigenous Patagonian people. It was an all-metal, mid-wing monoplane. The heart of the fighter was a pair of late-model Rolls-Royce Merlin engines. Each of them delivered an impressive 1,800 horsepower. Visually and in terms of flight performance, this Argentine fighter closely resembled its contemporary, the famous British twin-engine de Havilland Hornet. The British aircraft was considered the fastest in the world in its class at the time, despite its mostly wooden construction. Pallavicino's creation didn't just challenge it in speed. It was also practically identical to the Hornet, in both its physical dimensions and gross weight. As we mentioned earlier, the development of this aircraft was fraught with incredible challenges and a whole series of major problems. In a desperate bid to save even a little bit of precious time, chief designer Pallavicino made a highly risky call. He decided to postpone crucial static ground testing and conduct it only after the aircraft made its first flight. Because of this, engineers had to take parts that were already prepared for structural tests and repurpose them for the actual flying prototype at the last minute. The most alarming part is that even later on, they never found the time for these essential baseline tests. Those structural test articles sat completely untouched for months of anxious waiting. On one hand, this approach might have flattered the designer's ego, since it implied absolute trust in his engineering calculations. On the other hand, it was a colossal risk to the test pilots' lives. A perfect example of this was when one of the early test flights almost ended in a fatal crash. The cause was basic human error. A worker carelessly drilled a hole in completely the wrong spot compared to the blueprints. Quality control missed the mistake, even though standard static testing would have easily caught a defect like that. But that was not all. The aircraft was scheduled to make its maiden flight before its creator even had the preliminary data from the wind tunnel tests. This was despite the fact that a scale model had been sent to the lab 6 months prior to the planned first flight. Since all the structural and aerodynamic stability calculations were supposed to be based on that data, the designer had to make changes practically flying blind. He relied purely on his intuition, technical knowledge, and years of experience. On top of that, under strict orders from upper management, Pallavicino was forced to run round-the-clock, 3-shift operations during the final months of development. That kind of assembly line approach is great for mass production, but it is totally unacceptable when you are hand-building a one-off experimental prototype. This forced the project lead to practically live on the shop floor, trying to personally oversee every step and catch the inevitable mistakes. The pressure was so intense that the team's best engineer, Pietro Montano, literally passed out at the factory. He had not left his post for 4 days and 4 nights straight. Pallavicino himself suffered such severe stress and nervous exhaustion that he developed a chronic tremor in his left hand for the rest of his life. Despite all these crazy hurdles caused by the constant rush, and plenty of other underlying issues that management preferred to sweep under the rug, the aircraft's construction ended up being surprisingly successful. During the final inspection, the engineers found very few manufacturing defects. The most serious issue turned out to be a slight flaw in the wing geometry. The right wing panel was misaligned by just 1.5 degrees. This was a direct result of the chaotic, simultaneous work of 3 different riveting crews working on the skin. Because of this slight inaccuracy, the aircraft had a minor tendency to roll right in flight. Looking at the final numbers, the design and drafting phases took about 70,000 man-hours. This was only 1/3 of the time typically spent on an aircraft of this type. The actual fabrication and assembly took roughly 370,000 man-hours, which was barely half the industry standard for an aircraft of that class and era. On June 8, 1948, just 10 months after design and production began on this ambitious project, the Nancu began its initial taxi trials. By mid-July, the chief designer made a massive commitment. He promised to get the aircraft flying, even though it still was not completely finished. For instance, at that point, it did not even have a functioning landing gear retraction system. But history rarely waits. On July 18, 1948, at 12:50 p.m., the chief test pilot of the Aerotechnical Institute, First Lieutenant Guillermo Edmundo Osvaldo Weiss, climbed into the cockpit. After a takeoff roll of roughly 650 to 800 feet, he took the Nancu up into the skies over the Argentine city of Córdoba for the very first time. The historic flight lasted 20 minutes. In that time, the pilot climbed using just 50% power and ran through a series of basic maneuvers. Weiss threw in a few steep turns, tested the aircraft's low-speed handling, and even induced a stall. The aircraft stalled at exactly 83 knots. With the initial test objectives met, the prototype made a smooth touchdown on the runway at the local parachute school. The debut of the new Nancu caused an absolute sensation in the local press. That July, several major Argentine newspapers ran dozens of glowing reports and front-page stories. These articles were completely wrapped up in a heavy dose of national pride. The journalists were so caught up in the excitement that they conveniently ignored one crucial fact. The lion's share of the credit for designing this remarkable aircraft actually belonged to Italian engineers and technicians. Looking past the media hype, however, the Nancu actually performed beautifully in actual flight. As later flight tests would confirm, it had excellent handling characteristics. Sure, like with any brand new airframe, a few teething issues popped up during those early flights, but there were far fewer of them than anyone expected. This was especially true given the incredibly tight and completely unrealistic development deadlines the Argentine military had imposed on the design team. Over the 2 weeks following its maiden flight, ground crews managed to install the landing gear retraction mechanism. They also ironed out a handful of minor technical squawks. However, time for proper flight testing was running out fast. The airplane only made 4 or 5 brief test hops. That was nowhere near enough time to fully dial in all of the aircraft systems. But by early August, a direct order came down from high command. The order was to ferry the fighter to the capital immediately. On August 8th, with Weiss back at the controls, the Nancu took off at 1:20 p.m. He set a course for Buenos Aires, roughly 350 nautical miles away. The cross-country flight turned out to be an absolute triumph. Cruising at an altitude of just over 18,000 feet at a reduced power setting, Weiss covered the entire route in exactly 55 minutes. His average speed was phenomenal for the era, clocking in at 350 knots. On certain legs of the trip, helped along by a massive tailwind, the fighter reached ground speeds of up to 420 knots. After touching down at the capital's airport at 2:15 p.m., the pilot was personally greeted and congratulated. Meeting him were the acting secretary of the Air Force, Brigadier Cesar Raul Ojeda, and the director of the Aerotechnical Institute, Brigadier Juan Ignacio San Martin. The very next day, August 9th at around 1 p.m., a major official demonstration of the Nancu was held at the airfield. This event was organized for the country's president, Juan Domingo Perón. Up in the sky, the new fighter was escorted by Argentina's first jet prototype, the Pulque-1, along with a Vickers Viking transport. Giving the crowd a real show, the pilot performed a high-speed pass right down the runway center line at an altitude of less than 10 feet. The sheer spectacle thoroughly impressed the Argentine leader. He personally thanked the chief engineer, Cesare Pallavicino. In recognition of his invaluable contribution to the nation's aviation industry, the designer was formally decorated. As soon as the aircraft returned to base in Córdoba, the Argentine government set their sights on a new, ambitious idea. They ordered the technical directorate to immediately prepare the Nancu for a grand European tour. Scheduled for late August, this intercontinental tour was meant to proudly show the world the major technological leap Argentina's aviation industry had made. By mid-September, the fighter was expected to tackle a grueling route. Taking off from Buenos Aires, it would route through Rio de Janeiro, Natal, Dakar, and the Canary Islands. After that, it would head on to visit Madrid, London, Paris, and Rome. To safely cross the Atlantic Ocean, the plan was to equip the fighter with external drop tanks. This would boost its range to an impressive 2,700 nautical miles. Furthermore, the schedule was set up so its arrival in Great Britain would perfectly line up with the celebrations for the founding of the Royal Air Force. These celebrations were taking place at Farnborough from September 7th to September 12th. Weiss was slated to be at the controls once again for this epic flight. The journey would cover a total distance of nearly 12,000 nautical miles. For the crossing, he would be escorted by two Argentine Air Force Avro Lancaster heavy bombers. On the ground, during the stops in major European capitals, technical and diplomatic support for the crew was to be overseen by the deputy director of the Aviation Institute. This was Comandante Cesar Parradello Malcon, along with a familiar face, engineer Cesare Pallavicino. Despite the immense interest in this ambitious project, the government simply could not get the program off the ground in time. The main reason was that the aircraft was still far too unrefined. Right from the start, engineer Pallavicino openly opposed such a rushed timeline. He repeatedly warned management, both verbally and in writing. He warned that neither the aircraft nor its pilot were anywhere near ready to undertake the mission. At first, his warnings were ignored. However, by September, the flight program had to be put on hold anyway due to severe budget constraints. Shortly thereafter, engineer Pallavicino was removed from his position as head of the department. This was a significant move. Just a year and a half earlier, the ministry had entrusted such a high-level post to a foreigner for the very first time in its history. Now, his authority was reduced to basic technical supervision over the production floor and a group of 20 designers. Almost the entire staff was essentially reassigned to maintenance duty. This was done to free up resources for the new Pulque-2 project. At the same time, Pallavicino was tasked with continuing to refine the old prototype. He was also overseeing the prep work for a production run of 210 Nancu fighters. This was an order that had just been placed. On the technical side, the aircraft showed only one serious flaw during testing. It had excessively stiff controls across all three axes, along with poorly balanced ailerons. The heavy control forces on the elevator and rudder were easily fixed with just a few simple adjustments. They did not even have to alter the control throws to sort it out. Overall, though, progress was moving incredibly slowly. Development was bogged down by a new and highly inefficient workflow. There was also a severe lack of test flights. It wasn't until early April 1949 that they finally got the control system working at an acceptable level. Over those long 6 months, the aircraft was grounded for weeks at a time. The only real highlight that brought any attention to the plane during that period was a flight to Bolivia. This took place between late October and early November 1948. The goal was to show off the Nancu at a major industrial exhibition in La Paz. This event was held to celebrate the city's 400th anniversary. On November 4th at 11 a.m., test pilot Weiss took the Nancu up over the high-altitude El Alto airfield. During a spectacular dive, the aircraft reached an impressive speed of around 485 knots. After wrapping up the demo flight, Weiss received personal congratulations from high-ranking Bolivian officials and the Argentine ambassador. As for the problematic ailerons, the team made fruitless attempts to fix the manufacturing defects. Eventually, they decided to completely redesign the mechanism. The engineers used this opportunity to introduce a brand new British development at the time. This was the spring tab. Its main job was to drastically reduce the stick forces for the pilot. It also eliminated the plane's nasty tendency to drop a wing due to the spring dynamics. Since this system was new and untested on this airframe, Pallavicino played it safe. He ran preliminary tests on the elevator first. The tests went incredibly well. As a result, the aircraft made its first flight with the redesigned ailerons without a hitch. This success happened even though the spring tabs were intentionally locked out for safety reasons during the initial flight. Fabricating these new parts dragged on for a very long time. Picture this. The plane finally took to the air with the new ailerons a full 14 months after the issue was first discovered. But the worst part was that they simply forgot to warn the test pilots. The spring tabs were still locked out. The chief designer had absolutely no idea that any test flights were even scheduled for the next 15 days. He was caught completely off guard by the official pilot report. Naturally, the feedback was harshly negative. To make matters worse, it was written in the most exaggerated, blunt terms possible. Pallavicino reacted instantly. He wrote 2 official replies, personally handing them to the director of the Instituto Aerotecnico. In the first letter, addressed to the pilots, the engineer calmly explained the situation. He stated that if the aircraft's handling felt worse, it was only a temporary side effect of perfectly understandable safety measures. In the second letter, he firmly pointed out a crucial detail. Without close cooperation between the flight crew and the engineering team, getting this airplane sorted out would be impossible. However, even these appeals went nowhere. For another solid 3 months, absolutely nothing happened. The aircraft just sat idle on the tarmac without making a single flight. In late April 1949, the director of the institute gave chief designer Pallavicino some extremely bad news. Due to budget constraints, full-scale production of the Nancu was completely canceled. From then on, all efforts and resources were shifted to a new project. This was the Pulky II. As a result of this decision, almost the entire engineering staff was transferred to the maintenance department. Pallavicino was initially left with just 2 designers, and later on, only 1. They had no choice but to keep working on the sole prototype. This was true even though there was no longer any hope of it ever entering service. The truth is, the fate of the Nancu wasn't sealed by technical flaws, but by internal politics and a toxic work environment. Most of the Argentine management and local specialists flat out refused to cooperate. They were openly jealous of the Italian engineers and saw them as a threat. On top of that, government officials were constantly rushing the project. They made excessive and sometimes completely unrealistic demands about how the aircraft should be built and operated. In such a tense environment, the airplane's actual and quite impressive performance was largely overlooked. This included its payload, speed, fuel efficiency, excellent aerodynamics, and structural strength. When it came time for testing, the Argentine pilots gave highly contradictory and inconsistent feedback on the aircraft's handling characteristics. But the legendary aviation engineer Kurt Tank, who was working under the alias Professor Mathies at the time, finally settled the matter. He ran a rigorous and exhaustive series of flight tests. Tank pushed the airplane through all sorts of extreme conditions. He flew on a single engine and simulated a complete loss of flight controls. He even used a stopwatch to measure how long it took for the aircraft's oscillations to damp out across all 3 axes. Interestingly enough, the Argentine pilots had never attempted this level of rigorous testing, despite repeated requests from the chief designer. Kurt Tank was a widely respected authority in aviation, and nobody could accuse him of being biased. His final report was overwhelmingly positive. The aircraft was deemed a success, and his notes only covered a few minor operational tweaks that were mentioned earlier. Wrapping up the story of the Nancu, it's worth pointing out that Pallavicino incorporated several clever design solutions that had already been proven on the Caproni C-A331. One of these features was a fuselage with a triangular cross-section. This earned it the nickname the Pear because of its distinct shape. The Nancu ultimately marked the end of engineer Pallavicino's remarkable career in aviation. The Nancu was a highly capable aircraft that just needed a little more development and tuning time. The historical record easily backs this up. For example, the aviation press at the time gave the project highly favorable coverage. The Argentine government even had serious plans to demonstrate the aircraft in Europe. But the biggest validation came when the president of Argentina publicly honored the designer. He proudly stated that the Italian engineers had brought great honor to the Argentine Republic with their creation. When discussing Pallavicino's success, you can't ignore his dedicated team. He was supported by talented designers Gaviraghi and Ferretti, along with engineers Pietro Montano and Quarti, who had all gained valuable experience working at Caproni. The team also included technical specialists Targhi, Bardi, Trabalsa, Fossati, Cerruti, Pastorino, Saldin, and Baldano. Furthermore, roughly 60 skilled Italian workers were involved in assembling the aircraft. From a technical standpoint, the aircraft's design was highly advanced for its time. It was a cantilever mid-wing monoplane, meaning it didn't require any external bracing. The airframe was of all-metal construction. It was built around a continuous twin-spar wing design that ran through the entire wingspan, making it incredibly strong. Slotted flaps, which provided excellent high-lift characteristics, were operated by a dedicated hydraulic mechanism. That mechanism was cleverly housed within the rear spar section, right inside the fuselage. The aileron control system utilized a conventional layout with rigid pushrods. The total wing area, including the section passing through the fuselage, came to about 380 square feet. The fuselage itself was all metal, and like we mentioned earlier, it had a highly distinctive pear-shaped cross-section. The structure consisted of two separate sections, front and rear. They were securely joined together just behind the second wing spar. The internal framework utilized omega section stringers. This approach allowed the designers to create a sleek, aerodynamic silhouette. It easily sliced through the air. The tail section of the aircraft was entirely metal. There were no wood or fabric components used. The horizontal stabilizer was mounted midway up the vertical fin. This blended smoothly into the rear fuselage to form a single integrated structure. The elevators and rudder were also all metal. They came equipped with automatic Flettner tabs. This significantly reduced control forces for the pilot in flight. The landing gear was fully retractable. This drastically cut down on aerodynamic drag. The main gear struts were cast from a high-strength aluminum alloy. They incorporated heavy-duty oleo struts. Interestingly, during retraction, the main struts rotated 90 degrees. They would lay flat inside wheel wells located directly behind the engines. The gear doors were meticulously designed down to the smallest detail. They fully enclosed the internal mechanisms, whether the gear was up or down. For braking, the aircraft relied on a reliable Dunlop pneumatic system. The 17-inch tail wheel was also fully retractable into the fuselage. The cockpit was smartly positioned just forward of the wing's leading edge. This provided excellent all-around visibility. It featured a frameless, blown plexiglass bubble canopy, ensuring nothing obstructed the pilot's view when scanning the sky. The aircraft was packed with some of the most advanced avionics of its time. Inside, it featured a full instrument panel for night missions. It also allowed for precise air navigation and gathering data during flight testing. The electrical system ran off a generator tucked away in the left engine nacelle. It was backed up by two high-capacity batteries. For communications, they installed a high-quality Bendix radio system. This sat alongside a reliable radio direction finder to assist with spatial orientation. To maximize range, the engineers distributed the fuel across 10 separate tanks. Standard fuel capacity came out to 787 US gallons. Inside the fuselage, right behind the pilot, sat 2 tanks. These held a combined 369 gallons. The remaining 418 gallons were cleverly divided. They were stored among 8 smaller tanks hidden inside both wings. If the mission called for an ultra-long-range flight, the maximum fuel capacity could be bumped up. It reached a total of 949 gallons. They also included a separate oil tank holding 53 gallons. Although weapons were never actually fitted to the prototype, its planned firepower was formidable. The lower nose section was designed to house 6 20mm Hispano-Suiza 804 cannons. For ground attack missions, a 250-kilogram or roughly 550-pound bomb could be carried. It would be mounted on a centerline rack right under the fuselage. The real heart of this aircraft was its engines. The airplane was powered by a pair of powerful liquid-cooled Rolls-Royce Merlin Phi 12s. Specifically, these were models 134 and 135. They were counter-rotating. Each one produced an impressive 2,058 horsepower. The engines were securely mounted to rugged steel tube frames. To efficiently cool these mechanical monsters, the radiators were built directly into the leading edge of the wing. They sat right between the fuselage and the engine nacelles. All of this incredible power was transferred to massive 4-blade de Havilland propellers. These measured a full 12 feet in diameter. They featured a hydraulic constant speed system and were equipped with full feathering capability. This was a crucial mechanism that reduced drag. It also helped save the aircraft in the event of an engine failure.